Welcome back, everyone. In this video, we're going to attempt to understand what LoRA is, which is low-rank adaptation for fine-tuning. And so LoRA is a technique to fine-tune large models efficiently. Instead of updating a full weight matrix W, we keep W frozen and learn a low-rank update. Wow, thanks for the definition. That really helped, right? So let's get into it. So when we train large language models, in each layer, remember, they have millions and billions of weights, and updating all of them with backpropagation is very time consuming, right? Because that means we have to calculate all the gradients for those billions of parameters. So that's where LoRA comes in. And instead of, calculating the gradients for all of the values in the weight matrix, we instead, for example, in this scenario, we break up W into two smaller matrices, B and A. And so whenever there is gradients that we need to calculate, we only calculate the weight updates for B and A, which are small matrices. So that way, we can essentially update the entire frozen W, which is a massive matrix with millions of weights. We can update it, but we don't update it by calculating the gradients for all the values inside of it. We just simply add or subtract to it the change in W, which is going to be the product of two smaller matrices, B times A. Okay? So essentially what you need to understand is we're not, calculating gradients for a large weight matrix. We're calculating gradients for smaller weight matrix, B and A. And then once we multiply B and A together, they're much smaller, so they're computationally more efficient. We then add or subtract the values to the original big W, which was frozen. Okay, so we get to update the big W without having to computationally, calculate all the gradients and update them that way. Okay, and if this didn't make sense, please don't worry, because we're going to be looking at a numerical example as well, so don't worry about it. Now, what is this lingo over here? Well, I thought I'd tell you because you might see this, but essentially this means that W is a matrix in the space of real numbers with K rows and D columns. Okay, and over here we have A is a small trainable matrix and B is another small trainable matrix. And over here you see that they are R by D and K by R. And R is essentially the rank. And in the context of LoRA, the R parameter, or rank, is the most important hyperparameter that controls the size and expressive power of the fine-tuning update. So instead of retraining all the billions of parameters in a large model, LoRA freezes the original weights and injects a pair of small trainable matrices, A and B, into that specific targeted layer. And the R defines the inner dimension of these matrices, meaning if the original weights are 1,000 by 1,000 matrix, the new matrices will be 1,000 by R and R times 1,000. Okay? And R represents a fundamental trade-off. A lower rank, example 4, 8, or 16, results in very few trainable parameter. The advantages are a significantly smaller file size and faster training, but it has less capacity to learn complex new information. A higher rank, so for example, if R is 64, 128, or 256, this increases the number of trainable parameters, giving the model more space to learn nuanced details from the training data. However, this comes at the cost of a larger LoRA file, and it increases the risks of overfitting, where the model memorizes the training data too closely and performs poorly on new unseen examples. Okay, so we're going to talk a little more about R later, but it's essentially a trade-off. A smaller R means we're going to inject a smaller weight matrix, B and A, but it's going to be faster, but it might not be as good. Whereas, the opposite, if it's too big, it might overfit and it's going to be slower. Now R over here over here, this means that R is much smaller than K or D, and K and D are the input and output to that layer. Okay, so when you have linear layers, the size of it is, for example, 4096 by something, and then the output is also going to be, 4096 by something. So where K is the input dimension of the layer and D is the output dimension. And so the effective weight becomes, so that's why W effective equals W. This is the original large W that we've frozen plus the change in W, which is B times A. So essentially, we're simply going to be adding B times A to the original W matrix. Okay, so it's essentially that simple. So only A and B matrices receive gradient updates. Now, why use LoRA? Well, as we discussed, full fine-tuning updates every weight tensor, which is expensive in memory and compute. And so LoRA reduces the number of trainable parameters by 2 is the minimum, but usually a lot more orders of magnitude. And in practice, it achieves very good accuracy at a fraction of the cost. So think of it this way, when you train a model from scratch, you can't use LoRA, right? Because then you have to, train to get all the weights and parameters. You can only use LoRA when you fine-tune a model, like what we're doing right now. Okay, because when we fine-tune our model, this W is going to have all the learned weights. So the Mistral model that we're fine-tuning now has so much information. It knows about the world wars, knows about mathematics, computer science, but it doesn't know about, our specific stuff that we want to fine-tune it on. And so we don't want to throw out this big W, which has all the cool information that it has learned, but essentially we just want to tweak it a bit and update it so that it fits to our needs. So that's why we simply add to it some of the, training that happens. And then when we get weight updates, we essentially add those weight updates to the original W. And we do that by multiplying B times A, which are the two smaller but trainable matrices. And so this is very important, okay? Only A and B, which are the smaller matrix, are the ones that receive gradient updates. And it's figured out in a way so that when you multiply B and A, and then you add the values to W, the matrices will, the matrix math will work out. Okay, so even though B and A are smaller weight matrix, when you multiply them together, they will essentially get you a matrix that has the same size as the original W. So you can essentially just simply do W plus change in W to it. But because they're two smaller, matrices, training them is a lot easier than if we had to, train the entire big, large W. And so I will see you in the next video where we look at a numerical example.